So I'm going to go through this alkenes topic test and maybe take you through some of my thinking. So considering the reaction between propene and hydrogen bromide to form the major product, which species is formed? So if we are to draw out propene, that would have a H on there, the reaction with hydrogen bromide, this hydrogen will go on to the carbon containing the most hydrogens, okay, which is going to be this carbon here. So the bond will break and the hydrogen will end up on this first carbon here, creating this secondary carbocation. And the one that has a secondary carbocation is this one and this one. And just looking, the hydrogen goes on to the carbon carrying the most hydrogens, which is not this one, so it looks like it has to be this one. Yes, that would be the case, and the Br would be on the second bromine, so the Br would be on the second bromine, which it would be here, but the carbocation's in the wrong place, so it's not those two, but it's C. Question 2, what's the major product of the reaction of butyne and hydrogen bromide? D is just deuterium, which is the isotope of hydrogen. So we can draw that out again. So if we've got butyne, so CH3, CH2, that will be a H, I'll put the H there, double bond CH2. So this is the butene. It's the same thing as we've done before. Instead of H, we've got D. It's going to be delta positive, delta negative, so the bond will break, the double bond here will break and give its electrons to the deuterium, and the bond between the deuterium and bromine will break, and we will form the cation, the secondary cation, because this deuterium will go on to the carbon carrying the most hydrogens, because D is just another form of hydrogen. So we'll have the hydrogen on the end and we'll get a secondary carbocation, and then the bromine will come onto that second carbon there. So we would have CH3, CH2, CH. That'll be our bromine, and this would be CH2D. Okay. Oops. So is there anyone that looks like that with a D on the end? Well, that's a D on the end, but a bromine on the other end. It's definitely not that. That's a D on the end with a bromine on the second. It's too far away. It's not that one. There's the D. There's the Br. Well, it looks like it's that one. Let's have a look at this. No, that's the other way around. This would be the minor product if we did that one. So it has to be this one. That should be D, I suppose. Okay. And then looking at question 3, the correct systematic name for this, you must draw it out. And let's have a look what we've got here. So we've got C double bond C, so I'll take that. CH2, CH3, I'm going to just draw that CH3 out there. So 1, 2, 3, 4. On this carbon here, we said that was a CH3, so CH3. 1, 2, 3. There's a carbon here, and that's got a hydrogen on it, and then we've got 2 more CH3s, so CH3, CH3. Let me count, I've got enough bonds. 1, 2, 3, 4 bonds. 1, 2, 3, 4 bonds around that carbon. 1, 2, 3, 4. Okay, so I know I've got the right number of bonds. Now I need the longest chain, and the longest chain, 1, 2, 3, 4, 5, 6. Okay, if I numbered it this way, 1, 2, 3, 4, 5, 6, that would be 3 butyrene. Let me that would be 3 butene, and then the substituents would be on carbon 3, 4, and 5. If I numbered it the other way around, 1, 2, and 3, that would still be butyrene, but the substituents would be on 2, 3, and this one would be 4. Okay, so I'm going to number it this way around because the numbers are going to be the smaller ones. So this would be 1, 2, 3, 4, 5, 6. So it must be some sort of hexene, hexthreene. So those two there would suggest it's hexthreene. So it's not any of those two. And is it 2, 3, 4 or 3, 4, 5? We've established 2, 3, 4 is the smaller numbering system, so it has to be C. Okay, looking at this one, what is not true? It displays geometric isomerism. Basically, it will show EZ isomerism. The fact that you've got two hydrogens on this double bond, this side of the double bond, that's not going to show E or Z. That won't show E or Z. So at the moment, that looks like it's not true. It forms an addition polymer. Yeah, most alkenes, in fact this alkene will form an addition polymer, so that's correct. It undergoes reduction. So reduction is, there's three definitions for reduction. One is the oil rig that we know. Reduction is gain of electrons, and actually we're not sure if it's going to gain electrons because we haven't learned any of that yet. The other reduction is if something gains oxygen, it's oxidized. So if it loses oxygen, then it will be reduced. So is this able to lose oxygen? Maybe. Or the other one is it gains hydrogen. So if it gains hydrogen, that would be reduction. And actually on this double bond we can add hydrogen using a catalyst. So H2 and a catalyst. We can add hydrogen to that double bond. So yes, we can reduce that. So that is correct. So by that method, gaining hydrogen, it undergoes reduction. It decolorizes bromine. Indeed it does. Bromine is a brown colour. It is the test for an alkene. So BR will add to that double bond. It will make us a dibromo compound, and this orange colour will disappear as the bromine disappears. So that is true. So I guess our very first one was the one that was incorrect. So question 5. Propene reacts with bromine by a mechanism known as electrophilic addition. What is meant by the term electrophile and by the term addition? So an electrophile is an electron-seeking species. So it's an electron pair acceptor. So electron pair, we have to have that pair acceptor. Okay, so it will accept electrons. If you'd said it was a species that accepted electrons, an atom that accepted electrons, or a molecule that accepted electrons, or an ion that accepted electrons, then that would also have been counted. But very simply, it's a species which is an electron pair acceptor. And addition. Okay, so addition, this is a reaction where you increase the number of substituents in the molecule, or where you convert a double bond into a single bond, or where two molecules form one molecule. So addition is where two molecules form one molecule. Is a simple definition, or you could have said where it's a reaction which increases the number of substituents in a molecule. Okay, you don't get anything else out of it. B. Explain why bromine, a non-polar molecule, is able to react with propene. So we can say that the The carbon-carbon double bond, CC double bond, is electron rich, or it has a high electron density. So there's a lot of electrons there, and it causes an induced dipole in the Br2. Okay, if you didn't say induced dipole in the Br2, from your diagram down here in this mechanism, if you showed a delta positive, delta negative bromine, then I credited you the 1 mark up here. So if you'd have drawn that as well, delta negative, delta positive, that would have credited you 1 mark, but down here. Okay, so let's have a look at this mechanism then. So we've got propene, so I'm going to draw this as H2C double bond CH CH3. You can draw this out fully if you want to. Probably fully is better. CH3. So let's go with this one. I'll get rid of this. And it's going to react with bromine. So I'm going to have my bromine here. This is going to induce this dipole, delta positive, delta negative. The electrons go from the center of that bond to that bromine there. So be very precise with your arrow. And then the electrons go from the center of this bond to the bromine there. Okay, so what I produce is I guess it doesn't matter where I put that. I'm going to create a secondary carbocation because it's more stable, and I'm going to be left with Br minus. Now I must remember that I have 2 electrons on that Br minus, so I'm credited for this arrow here, I'm credited for this arrow here, I'm credited for drawing this species. So that's 3 marks. The 4th mark for this is where the tail of the arrow goes from the electrons to the carbon. Okay, so it must come from here. So if you found you've got a little bit of a red wiggly line, it's because your arrow didn't go from the right place, and that is the 4th mark. And the name of the product is 1,2-dibromopropane. So 1,2-dibromopropane. Okay, so the polymerization of propene is addition polymerization. It's not additional. So it had to be addition. If you put additional, then it was marked as incorrect. We have this butene nitrile here. It says draw the structure of Z-butene nitrile. So this is E, which is where we've got the priority groups on opposite sides of that double bond. Z, zusammen, same side, I think of Z is same side. So these priority groups will be on the same side as that double bond. So on the same side of the double bond. So I'm going to mark the CH3 here and the CN. And the H would be up there, and the H would be up there. So that's my Z-butene nitrile. So identify the feature of a double bond that causes this stereoisomerism. You have restricted rotation around that double bond. Okay, so restricted rotation around the double bond. So basically these groups can't twist. So they can't twist like a pen. Okay, so the pen, they can't twist, so they are stuck in this position. It's due to the restricted rotation. Okay, and finally this repeating unit of the polyalkene used by addition polymerization of E-butene nitrile. So I'm going to draw this down here. The CH3 is up at the top, the H is up at the top, this H is down at the bottom, and the CN is down at the bottom. Okay, I've not got a double bond. I'm going to put the two lines in. That is the repeating unit. Oh, do you know what? I'm going to put that there because that hydrogen was floating. Okay, so that is the repeating unit, and that's what I was marking you for. If you put brackets, I ignored the brackets, but if you put an N, I marked it as wrong. A little bit later on I gave you the benefit of the doubt, but I'm just going to show you the textbook because I know I'm going to get lots of grief on this. So here's the textbook. So here we've got polymerization. These are 3 monomer units making a 3-unit polymer. Here's an equation, a balanced symbol equation. So we've got n number of monomer units making a polymer with n number of units in it. However, the repeating unit, I'll show you, it's on the next page. The repeating unit, it's here like that. So there's the polymer and there's the repeating unit. So if you didn't put that, I didn't give you the mark. If you put a bracket round it, I ignored it. If you put a bracket and an N, I marked it as wrong. And as you can see, this is the repeating unit and this gives us the monomer. Okay, move on. So question 7. The structural formula of pent-2-ene. Draw and name the geometric EZ isomers of pent-2-ene. So C, double bond C. I can see I've got a H on that side and a CH3 here. I can see I've got a H on that. And then it's a CH2, CH3. So CH3, CH2. Please don't write this as C2H5. I think I might have put, no, I might have even marked it wrong. C2H5 is the molecular formula. For these organic compounds, you must write out the CH3, CH2, so none of that, please. So that's one isomer, and then that's the Z isomer, and I'll do the other one, C double bond C. I'll put the H up there, I'll put the CH3, CH2 down here, the CH3 can go up and that will come here, and that's the E isomer. So if we name it 1, 2, 3, 4, 5, so it's pent-2-ene, 1, 2, 3, 4, 5, so Z pent-2-ene I think is what I've got. Z pent-2-ene, and this is E pent-2-ene, and it's 2 because I'm numbering it from this point, 1, 2, 3, 4, 5, as opposed to 1, 2, 3, 4, 5. So Z pent-2-ene and E pent-2-ene is the correct one for that. Pent-1-ene reacts with hydrogen bromide to produce 2-bromopentane as the major product. Outline the mechanism. Okay, I'll do that for you now. Here's pent-1-ene that I've drawn out. This is the hydrogen on this side. The double bond will break and we will form a bond here with this hydrogen, and the bond between the hydrogen and bromine will break and the electrons will go onto the bromine, and we're going to create a secondary carbocation because the hydrogen will go on to the carbon containing the most hydrogens. Okay, so here the hydrogen's gone onto the carbon containing the most hydrogens. I've created this secondary carbocation, and so I'm going to get a mark for this arrow here, a mark for this curly arrow here, a mark for the carbocation, and then I must remember to take the tail of the curly arrow from the electrons to the carbon. Okay, and we'll get a mark for that, so that's 4 marks. Identify the minor product. So this is the major product. The minor product will be when that carbocation is on the end, on the primary carbon. So the bromine would come here, so it would be 1 bromopropane. So 1, rather than 2 bromopropane, it's 1 bromopropane. And explain why 2 bromopropane is the major product. So the secondary carbocation is more stable than the primary carbocation. Okay, I put the answer in. So the secondary carbocation is more stable than the primary carbocation. That's 1 mark. And 2 bromopropane is formed via the secondary carbocation. That gets you the 2nd mark. So we've set it up like this. There's our double bond. This is sulfuric acid. So it's 2 OH groups on a sulfur and 2 O's. So this should say delta positive and this is delta negative. So this, these electrons go towards that hydrogen, and the electrons that go between hydrogen and oxygen are displaced onto the oxygen. Okay, so this hydrogen will go onto the carbon containing the most hydrogens, which is this one, and will create this secondary carbocation here. I'll just draw it for you now. Okay, so this is what I got most of the time, but you do have to have a negative charge here on this oxygen, and you do have to show the lone pairs. Where it doesn't matter where this negative is, you know, you could have located it somewhere else, but this whole molecule has to be negatively charged, but I've located that negative charge on this oxygen here. Okay, so now we've got this carbocation, so these electrons create a bond with that carbon, and that's the carbocation carbon. So where do we get the marks? We get the marks for this arrow here and a mark for this arrow here. We get a mark for the carbocation, and we get a mark here for showing the correct bond formation, and then we can draw this out if we wish to get this final product, which is this one, because it's just stage 1 that we're doing, but that's what we've got. So state the overall role of the sulfuric acid. Well, we're going to get the acid back. It's a catalyst. Okay, so this is worth 1 mark, this is worth 4, this is worth 1, this is where you get the 6 marks from. Question 9. Reaction scheme shows the conversion of compound A to compound B, so by that same mechanism, and then it forms compound C. The structure of A is shown. Circle the carbon atoms which lie in the same plane. Remember, this is planar, so these two lie in the same plane, but it's trigonal planar, so even around here this is trigonal planar, so this is in the same plane as this carbon, as is this carbon, so these three carbons and that carbon are all in the same plane. Okay, now I'm going to get grief for this, so I've just built you the molecular model. So here is the double bond, and you can see that this carbon and this carbon are in the same plane as this, which is in the same plane as this. So if we turn it on its side, you can see that they're in the same plane. Okay, I can lay it flat, and these carbons are in the same plane. This carbon here would be off to one side, so I'll just put a carbon on. So here you can see that that carbon's not in the same plane. That carbon is tilted down. Okay, so we're tetrahedral around here, and it isn't in the same plane. So it's just 1, 2, 3, 4. They're definitely in the same plane, and this carbon just moves around and isn't. So it's 1, 2, 3, 4. It wants the mechanism for the reaction in step 1. It's just the same as this mechanism, but using this molecule. Just remember, when you add the hydrogen goes to the carbon containing the most hydrogens, which will be this one, and you create this carbocation, which on this carbon, which is a tertiary carbocation. You've got 1, 2, 3 carbons around this carbon, so this is tertiary, which will come into play a little bit later down here. So that mechanism is the same as one we've done earlier. So state the reagents and condition used in step 2. So step 2 is this part. So we can see what we're doing is we're removing this sulfate group here, this hydrogen sulfate group, and putting an OH group on there. And how do we do that? We add water and we reflux. Okay, so the reagent here, it could be a couple of different reagents, but water is the one, and it's reflux. And the name of our compound is 1, 2, 3, 4, so it's a butanol. So 1, 2, 3, 4, 1, 2, 3, 4. So it's butan-2-ol. There's a methyl group, 2-methyl butan-2-ol. So 2-methyl butan-2-ol is the answer to that one. And then when compound A is converted to C, a second alcohol D is also formed. Well, that will be because instead of creating the tertiary carbocation, we create the primary carbocation. So the hydrogen doesn't go onto the carbon containing the most hydrogens, it goes onto this one instead. So we create a primary carbocation, very unstable, so we don't get much of it. So here it's asking, alcohol D is isomeric with C. Well, it will be. It's just that the alcohol's on a different group. And it's as a minor product. Identify alcohol D and explain why it is formed as the minor product. So this will be 2-methyl butan-1-ol. And here we can say this is formed from via the primary carbocation, which is less stable than the tertiary carbocation. Now, a few of you actually put it's less stable than the secondary carbocation, which is true, it is, but this is not a secondary carbocation, this is a tertiary carbocation. So you needed to refer back to that. So I was looking for this tertiary carbocation. So you got 1 mark for the 2-methyl-butanol, 1 mark for saying it was via the primary carbocation, which was less stable than the tertiary carbocation. So there's the 3 marks for that one. Okay, and we're back to the polymerization again. So this is just a repeat of the previous question. Type of polymerization, this is addition, not additional unit, not additional. The repeating unit for this, so if I were to draw this, that would be a H, that would be a CH3, and 2 CH3s here, CH3, CH3. So that's the monomer. If I put the double bond there, it's a repeating unit, so I'm going to draw the lines. That's the repeating unit. If you put a bracket and an N this time, I did give you the benefit of the doubt just because I didn't want to penalise you for the same thing twice, but this is your repeating unit. Draw the structure of an isomer of G which shows geometric isomerism. So if we look at this, let me draw G out for you. So we've got double bond, CH3, CH3, H, CH3. Now that's G. That doesn't show geometric isomerism. Geometric isomerism wants EZ. This is, and it wants the isomer of this. Because we've got 2 CH3 groups here, we've got no priority. So what we'd like to do is to try and get a priority group. And the way we can do that is we don't want 2 CH3s, we want 2 very different groups here. So if I draw my, I'm going to keep this side the same, but this time I'm going to move this carbon to here. So CH2, CH3. So I'm going to move that carbon to here, and I'm left with a hydrogen. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep. So I've got the same number of carbons. 3, 6, 9, 10. 3, 6, 7, 8, 9, 10. I've got the same number of hydrogens. So this is definitely an isomer of this. This has got one priority group and another priority group on opposite sides of the carbons. So this is going to show EZ isomerism. So this is the structure we're looking for, not that one. So draw the structure of an isomer of G which does not react with bromine. So basically, if it does not react with bromine, it does not have double bonds. So 1, 2, 3, 4, 5. Put it in a ring. 1. So CH2, 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 CH2. 1, 2, 3, 4, 5, 2, 4, 6, 8, 10. Okay, so that's cyclopentane. You could have drawn it like, whoops, that as well. You could have had methyl cyclobutane. You could have had dimethyl cyclopropane. The number of different things. Okay, so any one of those, they're unsaturated, sorry, they're all saturated and they won't react with bromine. So anything that doesn't have a double bond, and you tend to think of cyclo compounds.